Welcome to Learning Intention 5, the normal distribution. The distribution of a statistical dataset or a population is a listing or function showing all the possible values or intervals of the data and how often they occur. A normal distribution is an idealized, smooth, bell-shaped curve with all of the randomness removed. It represents a data set that has most data values concentrated in the middle of the range, with the remaining numbers trailing off symmetrically on both sides. For normal distributions, the probability distribution is continuous. The frequency density curve is characterized by a symmetrical, single-peaked, bell-shaped curve. So this guy over here. It is fully described by the mean and the standard deviation. Now the standard deviation is a measure of spread. So think of about how the data it's all spread out. It's a measurement of how it's spread. There are two symbols for standard deviation. The first one is the Greek letter sigma, or I should say lowercase sigma. And we also have the Roman alphabet symbol S. Now both of these represent two different things. Firstly, the sigma represents the population standard deviation, and conversely the letter S represents the sample standard deviation. So the sigma meaning the population, so if we know all of the spread of the entire population, and conversely S represents the sample standard deviation. So say if we've taken only a portion, so sampled only a portion of that population. Now, a standard deviation is the difference between an individual piece of data and the true mean. And again, we have two different symbols for this. We've got the letter mu, sounds like an M in the Greek alphabet, or we've simply got this X bar. The Greek one, so the mu, is similar to the sigma in that it's representative of the population, so the population mean. Alright, the normal distribution is also characterized by the 68-95-7 rule. Approximately 68% of the data will lie within plus or minus one standard deviation of the mean. Approximately 95% of the data will lie within plus or minus 2 sigma or 2 standard deviations. And approximately 99.7% of the data will lie within plus or minus 3 standard deviations. Visualizing this, what we find is that say we've got this beautiful bell-shaped curve here. If I draw a line down the very center here, then what we find is that this line itself, it's indicative of the population mean. Now if I get a second line, and I'll use, let's go purple. If I draw this line here, and we say that this line this line, they're approximately one standard deviation away from the mean, so that can be interpreted as the mean mu plus sigma, and the area underneath this curve is, or underneath these curves between the lower and upper bound here, is going to be 68.26%. So this if I shaded this area in here, it would compose 68.26% of all of the area underneath the curve. Now if we go a little bit further out, and let's say we go here, do straight lines, and here, these are going to represent 2 sigma. So it's going to be mu plus 2 sigma, and mu take 2 sigma, or 2 standard deviations. And what we find is that 95.44% is captured by this area here. So if I shade all of this area, we'd get 95.44%. And finally, if we go out to 3 sigma, then it's going to be mu plus 3 sigma, take 3 sigma. Then we see the population here sort of running out of space, roughly like so. And just finally, what we find in the outliers in this little area here, this would be roughly 0.13% in this tail here, and you'd also see the same represented over here as well. So basically what this curve does is it's a nifty little tool of describing the population itself, so the spread of it. So we can come to a few conclusions here. Using this particular graph, what we find is that the mean, the median, and the mode, so mean being the average middle number, the median being the actual middle sample, and the mode being the most common, they're all equal. Secondly, the graph itself, you might have been able to notice it, the graph itself is asymptotic to the x-axis, as in it doesn't go underneath the x-axis. It doesn't go into the negative y values, which I should have put a f of x there. So it doesn't go into the... And then finally, the area between the probability density curve and the x-axis is equal to 1 square unit. So if we shade all of this area underneath the curve here between the x-axis, that would all sum up to 1, or 100%, so just 1. Alright, moving on. Okay, so that's been quite a lot of theory. Let's look at how we can actually use this new tool that we're starting to learn. So what we can say is that if x is a distribution of a continuous random variable which follows a normal distribution with mean and standard deviation, then to describe the distribution mathematically, we can write the random variable x is distributed normally by mu, or mean, and the standard deviation. Great. Let's go down and we'll have a go at a few examples. Alright, a Coca-Cola vending machine advertises that it pours 250 milliliters per pour-up and is set to give up or give a main fill of 260 milliliters per cup. The amount of Coca-Cola is normally distributed with a standard deviation of 15 milliliters. Write an expression for the distribution. So the two key pieces of information here is the main fill of 265, and we also have the standard deviation of 15 milliliters. So mean fill, so that's 265 milliliters, and standard deviation sigma is equal to 15 milliliters. So it's asking write an expression for the distribution. Well, if we use what we've just had a look at here, the random variable x is distributed normally with mean and sigma, or mean and standard deviation, then we can simply rewrite it like that. So the random variable x here is distributed normally, and in this case our mean, or mu, is 265. And our standard deviation is 15. Alright, that's question 1 done. Right now it doesn't look very helpful, but it will be helpful. Let's go down. Part B. On the curve of the normal distribution below, show an appropriate scale on the horizontal axis and label the curve. So what this question is asking is, we've got a random or a standard normal distribution here. It's asking us to label this particular curve in context to our problem. So the fill rate or the pour rate of the Coca-Cola vending machine. Now looking at this, we know that at the very center of this bell curve is going to be our median and our mean. And if we already know our mean is 265, then I can just go ahead and label it 265 like that. Now, the next part of this is we have to label the other values. Now, going across one standard deviation, we know that, well, if the mean is 265 and one standard deviation across is going to be plus 15, then we find that mu plus 1 sigma is going to come out to be 280, like so. And similarly, if we go the other way, if we go 265 take 15, then we're going to get 250. Now, what does this actually mean? Well, it means that, well, if we add these two together, we're going to get roughly 68%. 68% of the cups poured are going to be between 250 and 280 milliliters. So all we're doing in this particular question is just annotating this curve to reference our particular problem. Now, if we're looking at the two standard deviations, then it's going to be 280 plus 15. Well, that's going to be 295. And for two standard deviations to the left, then that's going to be 235. Finishing it off, 3 standard deviations, well, that's going to be 310, and minus 3 standard deviations is going to be 220. Well, what does that mean? Well, remember that this is represented by 0.13, so 0.13% are going to be less than 220 milliliters when poured. Okay. Now, jumping into a few questions. Part C, use the diagram in Part B. Okay. Find the percentage of randomly filled cups that contain between 265 and 295 milliliters of Coca-Cola. So it's asking for the probability. So we can write that as the probability of 265, our random variable here, 5. So our random variable is between 265 and 295. What's the probability of that? Well, looking at our curve, we locate 265, which is there, and 295, which is there, and we have to add the area in this curve there. That wasn't very clear, was it? We have to add the area that's represented in here. Now, if we want to be really specific, then we can grab the values, and we know that the area in this little section here, that's going to be approximately 34.13 if we want to be quite pedantic. And the area that's represented here is going to be 13.59. Now, if I grab my calculator, let's bring in the calculator here. Okay, yep. And we're going to go 34.3 plus the 47.72. So what we find is that the percentage of randomly filled cups between 265 and 295, well, you're going to see 47.72% of the pours between 265 and 295. Now going down, customers can put in a complaint if they receive less than the advertised 250 milliliters. What percentage of customers that use the vending machine could complain? So again, we're going to use this chart here to calculate how many complaints we could possibly have. So what we need to do is receive less than 250 mils. So, alright, probability of random variable x being less than 250. What we need to do is locate the area under the curve that is going to be represented by pause less than 250. Well, we've got 250 here. We're looking for this area here, here, and finally in there. So that's going to be, first one is this area here. That's going to be 13.59 plus the second area in here. That's going to be 2.15 plus the final area, and it's really small, it's only 0.13. Now if we sum all of those together, we find that our total area is going to be 16.17%. So yeah, quite an alarming amount of complaints that we could be fielding there. Okay, moving down. Find the probability that a randomly filled cup will contain between 240 milliliters and 270 milliliters. Alright, so like before, let's set it out. So we'll go probability 240 less than 270. And this is where we hit a problem. Notice we don't have these values explicitly put on our graph here. So this is where we really need to use our technology. So have a look at this. We've got some instructions here on how to use our Casio calculator to do these non-standard values. So what I'm going to do is I'm going to exit this matrix mode. And I'm going to press 2, or I'm going to go across to statistics. Then I'm going to go menu and then into stat. Actually, I've done that. F5, so distribution, and then F1 into normal. And then we're going to go F2 for normal. Okay, now we simply put in our values. So we're going for a lower value of 240, upper value of 270. And remember, our standard deviation is 15, and our mean is 265. Yeah, this number here. Putting that in, go down to execute, and it's going to be this here. So probability is 0.5827683. So we put that as 0.583, and then writing that as a percentage, we'll say it's roughly 58.3%. So 58.3% of the cups will be filled between 240 milliliters and 270 milliliters. Looking at this curve here, what's that going to look like? Well, that's 265, then 270 is going to be somewhere like there, and 240, let's have a look up. So reference, it's going to be a little bit less than over a standard deviation. So we're saying that area in there. Okay, so going down, find the proportion of cups that are likely to contain less than 225 milliliters. So 225, it's somewhere between 3 standard deviations and 2 standard deviations. So substantially under. We're looking for the area here, which means that it's not a lot we're looking for. So again, setting it out using our notation, we simply go for the calculator on this one because it's a non-standard number there. So just go to execute, and we're looking for contains less than 225. So our lower limit, we'll just set it to 0. And then our upper one, we'll set it to 225 because this is the upper limit. Now, the reason I chose 0 is because we're looking for something hugely or very, very small. So basically, that's the only reason I chose 0. I want something to be the absolute minimum it can possibly be. The 15 and 265, we don't have to change those. Executing that, we get an answer of 3.83 times 10 to the negative 3. And what does that convert into as a fraction? Well, or as a percentage? Well, it's 0.383%, like so. So what we find is that the probability of getting a cup filled that's less than 225 milliliters is unbelievably small. In fact, it's it's so small you'd very few you'd actually see like that by the looks of it. Okay. Now F, if the total capacity of a cup is 300 milliliters, find the percentage of the cups that will overflow. So again, where are we? The fill rate is 300 is going to be somewhere in between there. So it's between 2 standard, or plus 2 standard deviations and plus 3 standard deviations. So again, quite large. So what we're looking at is the probability that X is greater than 300. And using our technology once again, we simply change it. So the lower limit is going to be 300. And then we want to set the upper to something humongous. So in this case, we'll just set it to, we'll go something big like that. Going up, then let's go execute. What we find is it's roughly, probability is 9.8353 times 10 to the negative 3. That'll do. And then converting that to a percentage, will 0.982%. So once again, something quite unlikely to occur. So that brings this video to an end.